It's great to be back again. Love presenting at the IoT Slam, and really love presenting on, as I think anyone that's ever seen any of these presentations of mine before, my favorite subject, which is security, trust, digital trust, particularly as it applies to industrial systems today, because that seems to be the area in which we need to do the most work as an industry. And the trouble with today's systems, of course, is that they're designed with the notion of effectively a moat, a perimeter-based security system. And for a lot of applications, this works just fine. In fact, any one of us that is working for any kind of corporation and any of us that have any digital sense in the home live and work behind a firewall. In fact, usually behind a system of firewalls, not just firewalls, but intrusion detection systems, prevention systems, security incident and event management systems. There's a whole layered cake of providing protection in the metaphor and in the structure of castles of old, where you would have a moat and high walls, but once within that perimeter, all bets are off. And that's where attackers and threat actors have been very, very effective. Once they get inside that perimeter, they have access to everything, and they're able to then go through their kill chains, moving laterally, escalating privileges until they completely take over an entire network. It's the new way things are done, it seems. Advanced persistent threats will sit in your network until they've basically owned everything within it. I like to call it eggshell defense, because I think the metaphor is really very apt. Very brittle outer core, but once attackers are inside, they get access to all the goodness with almost no restrictions on their movement or their ability to transition to new targets and further their aims. Over the last few years, there's been a new approach, an old approach that has been layered as new. A lot of the principles here have been espoused for, at least the last 28 years I've been working on digital systems, verifying everything within any secure system. And anyone from the smart card world, certainly the world of huge networks, cellular networks, app stores, trusted app stores, things like that, we'll see all these principles as really quite familiar. But what we need to do now as an industry, especially an IoT industry, is to take these best practices, extend them, and adapt them for the more difficult environments of the IoT, where the threats are more serious and the impacts are considerably more serious. And so now we have to start treating our industrial systems, whether it's in the grid or even in our homes, where we're doing a lot of energy management with batteries from electric vehicles, often photovoltaics on the roof, management within the home to be part of the grid, to optimize and harvest energy savings, all the way up through distribution, all the way up through generation. All these systems today are really left in very much of the perimeter-based paradigm of the past. And that's why we're seeing just so many attacks, so many successful attacks, because it's become so effective to turn the lights off on an adversary, and much worse can be done. There are 4 key tenets for what is now called, in this umbrella, zero trust networking architecture. First of all, trust no one. Trust nothing, no one on the internet. Verify everything. No entity is trustworthy by default. Every access request must be scrutinized and fully authenticated. And that in and of itself will protect to a large degree against the persistence of threats staying within a network, because it is no longer guaranteed, if this is properly applied, that once an attacker is in, that access will be maintained. And then for every access, provide the least privileges, not the most. And it can be a bit inconvenient because this can now mean that systems, machines, users may be locked out of something that they previously had access to, and they might have to ask for explicit rights, or maybe they were accessing rights they were never intended to have in the first place. So users and devices, each of them is given just the minimum access required to complete whatever the function or task that they are involved with on the network. So unauthorized access should be reduced or eliminated. Now, like any good ship at sea that has bulkheads, anticipating that there may be a breach somewhere in this ship, you don't want that single breach to sink a ship. So for a long time now, there's been segmentation, bulwarks within a ship's hull. The same concept needs to be applied within our networks today, dividing networks into smaller and smaller segments so that threats can be isolated. And if there is a breach, lateral movement is very, very difficult. We can also apply the first two principles to each one of these segments: trust no one, verify everything, and applying. And ultimately, at the end, it's never done. The attackers never fall asleep. It's a 24/7, 365 endeavor to protect your systems. So vigilance is critical. And what that means in this day and age is real-time monitoring and evaluation requests, the traffic, behavior, identifying threats. And all of this really has to be done with automated systems. It's too much to be done manually because, for no other reason, the attackers have very sophisticated automated systems. And so we need to be able to meet them where they are on the battlefield of this cyber game, if you will. Now, by adopting these core zero trust architecture principles, organizations can fortify the security, enhance adaptability. I'll talk a little bit about that in the slides to come. Simplify compliance, which has become more important than ever before, and reduce the complexity of the networks. Now, if something this important is at stake, we can't afford to take anyone at their word. But if we can judge their actions by observing their behavior, and a working level of trust may be established. So this is this principle of trust no one, verify everything. Now, least privilege under a zero trust architecture, what that really means is that if I need access to read a web page, I shouldn't be given access to write to that web page. And that's probably one of the most innocuous but simplest examples in all of this. It also applies to an application. If an application needs GPS, for example, it's a mapping application, they would be given access to that GPS, but there's no reason why they should be provided persistent access to that GPS when you're no longer running that applications. And that's something that all of our smartphones have run afoul of. The applications on, I bet you everybody's phone is actually doing a lot more than we'd really like them to. And even within our consumer realm, we're seeing that's hard to apply. You can imagine the destruction that could be caused in an industrial realm when privileges persist when they shouldn't. Now, ultimately, what security and trust systems are all about is asserting your intentions and inserting your intentions in terms of policy and encoding that within policy, and then ensuring that the organization, both its humans and its data and its actual machines, all comply within that umbrella. And so the types of policies you want to apply, getting into some of the details here, number one is persistent data protection. It's no longer enough to just have what I kind of like to call pipe protection of data. It's no longer enough just to have a TLS pipe from a client to a server. Mutual TLS is good because at least now you're authenticating each of the endpoints. But you know what? When the data's sitting on the origin endpoint, and when it comes out the other side on a load balancer, for example, it's exposed. And exposed data gets manipulated, it gets changed. It could then be used to mount further attacks by injecting malware, things that could cause a buffer overflow, for instance, so that there's a potential for remote execution attacks. But also, today, the provenance and the quality of data is really, really important for educating our machine learning systems. And so to protect against the poisoning of our our AIs, we have to ensure that persistent protection of data from where it's generated through whatever networks it goes through, whatever gateways, whatever routers, until it reaches the other end. It's very analogous, I think, to the breakthrough that pretty good privacy PGP provided to us in the 90s, which allowed people to communicate securely across a bunch of routers and gateways that weren't necessarily trusted. And a lot of people today imagine that if they use Google Mail, Gmail, or something like that, they're all the same, Outlook or whatever, that because there's some security within that link, that's enough, but it's not. It really has to ensure in an adversarial environment, which we see in the IoT, especially in operational technology, absolutely you have to keep that persistence of data protection, and the data has to be protected itself. So it has to be protected within a protected processing environment. From there, be able to go through whatever networks, through whatever gateways, routers, other intermediate machines, and then only processed in another protected processing environment using good cryptographic systems. And if you're able to do that, and really achieve that PDP, that persistent data protection at rest, in transit, and use, then you can layer on other functional capabilities like authorized commands. Commands arguably are much more sensitive than the actual sensor data or the observation data that comes from the edge of the OT. Be able to send commands to, for instance, change the pitch of a rotor blade of a wind turbine, for instance, or to change the RPM, the speed that it returns at, or to stop it, or to start it up. All these are very sensitive things, and especially in a system like an energy grid, because of the requirements to keep everything balanced, in and of themselves, those can cause serious problems. And it's not limited to energy systems or just electricity systems, I should say. Oil and gas also has very strict sensitivities because things could blow up. When you really think about it, it really applies to all of our critical infrastructure, our water systems as well, for distributing good, clean water and not losing too much, and ensuring that's actually protected as well. As I was saying before, we want to do a lot of segmentation to slow down the lateral movement. What I'm seeing a lot in my practice is that there's very strong, albeit brittle, eggshell defense that is applied to protect the systems. However, once an attacker gets under the wire, then it's not very hard for them to move from one machine to another within a network. Very few enterprise networks and very few OT networks are microsegmented internally as well. And so not only can you actually create these barriers for lateral movement across the system, but you can also apply specific policies, specific privileges to each of those segments. So you can tune very, very nicely the least privilege elements of your network. Now, of course, each element has to have limited access. Only by explicitly granting access should there be access provided. So each segment only allows access to the resources required for its functions, and that is in and of itself reduces attacker mobility. The containment of breaches is critical. A breach in one segment doesn't go into another one, thanks to that isolation. And this last point here, and it's one I'm going to double click on in the coming slides, because I think it's really important. And if there's one thing you take away from this talk and what I'm sharing with you today, is the notion that the way things are done today does not have to be the way they work in the future. What we see all the time in industrial control systems is air gaps. The notion that the enterprise system, the IT system, it is a riskier environment. It has a higher attack surface. It has all us users involved with us. Us users could receive phishing emails that are very, very sophisticated today. We can even let backdoors into our network accidentally. So notionally, to firewall off the operational technology and keep it in a secure enclave has been the way that things have worked. But everything since Stuxnet 20 years ago, we've seen that air gaps don't work. And in fact, when you talk to the Department of Homeland Security in the United States, when they go around and they do their audits, they find that every single time that an OT network is breached, or sorry, not breached, is ostensibly air gapped, it's actually connected through multiple connections. And that's why a couple of years ago, the Colonial Pipeline, it had an enterprise ransomware attack, but they weren't confident at all in their air gap to their OT. So they shut down the entire pipeline from the Gulf of Mexico to Boston, cutting tens of millions of people off from gasoline and power. Thank goodness it wasn't in the winter. But this idea of converging between OT and IT, the time has come. We have the technology. If we apply the zero trust networking architecture principles, we can trust environment. We can bridge trust between environments. And that will usher in, that will be the catalyst for the convergence of OT IT systems. And today there's tremendous inefficiency in our OT systems because the people running them don't have the visibility. Ironically, Apple probably has more insight into, how smart homes work than a big utility will have insight into how their turbines, the distribution of energy, and their consumption of energy work. This blind spot really makes it difficult for us to make the most of our limited energy resources, makes it very difficult for us to transition from fossil-based fuels to renewable fuels because they're so data-driven. And if we were able to do that, this convergence, then we could start running our OT systems with the sophistication that we now run our IT systems. Talking about homes and smart homes, they're more and more become a part of the energy mix. They actually represent a significant part of the energy load, and our transition to green fuels really require us to incorporate the homes as part of the overall system. Homes are hostile. Homes have all sorts of IoT devices from different manufacturers, all sorts of Wi-Fi hubs. Very few homes have a CISO in residence to be able to set up a hardened network and apply zero trust networking principles. And so bridging into that environment is a challenge too, but with the technologies of distributed trust systems, we could do that too. With distributed trust systems, paired with zero trust networking architectures, they could be brought into the fold in a trusted way too. And for those systems, there's old SCADA systems, Modbus systems that really still are being amortized because they're multi-million-dollar systems. They're going to be with us for quite some time to come. There are ways that you can microsegment them into their own environment, but then twin out their capabilities. So you interact with a twin in a highly hardened environment in the cloud or the edge cloud to be able to manage those as well. So we can take these three environments, converge the trust model among them, and really reap tremendous benefits in terms of energy savings and transition and just more efficient performance of our OT systems. So I'm going to continue on some of these principles that, if we were to apply them, would allow us to provide and enable and catalyze this convergence between different trust environments. There's a big problem with zero trust attacks today. Pegasus is spyware, which is very, very effective. If a bad actor sends you a Pegasus-laced, malformed GIF, a little animation to your phone's going to receive it. And unknown to you, in the background, that animated GIF is blowing up your phone. It's causing a buffer overflow and causing the bad actor to literally get root at layer 0 to the kernel of your phone and basically own it. Not just be able to monitor your movements, but to also view anything that you're seeing through your camera, to be able to use all the sensors on your camera, including your microphone. We're seeing these attacks, these zero authentication attacks, come in as well in operational technology systems. So attesting to the hardened and the good stature and posture of your system, your device, before you communicate with another, will become part of this mix to ensure protected systems. I talked earlier about eternal vigilance, always monitoring, never letting your guard down, and that really falls down into 4 key principles: the don't talk to strangers, entity attestation, persistently protect data, to have common command frameworks that have authorization and the cryptography behind it to enforce it, and this principle that all endpoints need to fend for themselves, with the possible exception of those really old legacy systems. But the principle should be that endpoints can protect themselves. And you know what? The technology of today really enables that. The benefits that you derive from a zero trust architecture system are many. You start off with the fortified security. You have a more secure system fundamentally. Not only one that is increasingly fortified, but one in which you can really observe different segments in different areas, and you can actually be able to observe attacks as they're in process. And it's much easier to set up sacrifice or enticing elements, like, for instance, honeypots. Or honey networks even, and to be able to monitor how actors move through that while you keep your secure systems offline and completely segmented away from those. Also, being able to scrutinize each access request requires the processing to be able to do that, but to enforce limited privileges on those unauthorized accesses will eliminate or really come to the point of, I'd say, reducing to eliminating data breaches to transform the way things are done today. This approach of being very, very granular enhances adaptability too. So that flexibility allows you to move different parts of the network around securely and to know what's happening with it. If you're always encrypting data at rest from when it's generated, protecting it persistently all the way through to where it's consumed, that also gives you flexibility, because now you're really worried more about the endpoints and not where they're physically sitting or where they're logically sitting with respect to your various protection devices. The devices protect themselves, they protect the data implicitly, the data is implicitly protected and governed until it's consumed ultimately wherever else in the network it's consumed. And this can also apply to heterogeneous networks and multi-party networks, and more of the IoT. For instance, a utility will have a fleet of equipment providers, and to have that interoperability in the trust model allows us further that flexibility. This common trust model with this really granular approach and persistently protecting makes everything easier in terms of a system provider and service provider point of view. Because you continually monitor each one of these granular little bits in your network, no matter where they are, it provides for continuous monitoring and evaluation facilities, and that facilitates regulatory compliance. There are tools that you can plug into these monitoring logs, and they effectively demonstrate and show evidence that you're applying all your policies in the way you stated. They've been reduced to practice in the form of procedures, and that you have specific controls in your control set applied to mitigate the risk, and the residual risk. All of that is automated and tabulated and provided for third-party auditors to prove and certify the compliance in. And that's something we're very familiar with at Intertrust. We've been audited for many years, well over a decade, so 14 years. And that's why we have certifications like WebTrust and others. And as I said earlier, this really reduces the complexity, eliminates the need for multiple security solutions. It streamlines all of your infrastructure. And so to wrap this up, I think the 5 key ideas that really that I hope you remember after this. These are the principles that I live with day in, day out, as both protecting the intertrust network as well as applying these principles to the designing of the new trust systems that we're doing for the IoT. Number one, of course, is implement zero trust architecture across all your systems and architecture. Can't leave anything out. Remove the reliance on perimeter defenses and what you could say almost blind trust. Apply attestation so that you can be certain of the provenance and trustworthiness of any system or device that's trying to communicate with you, your users, your devices and systems. Continuously authenticate and authorize all users, all devices, all systems, all actions. Trust but verify, and continually verify. Adopt the persistent data protection I mentioned earlier. It isn't enough to protect data in transit. You need to protect it while it's in processing, as well as while it's at rest throughout the system. And that applies to data generated, not just data lakes and things like that in the cloud. It has to be protected right at the edge where the data is initially generated to ensure the provenance of that data for AI as well. And of course, all commands in the system have to have a cryptographic authorization framework to ensure the provenance and the validity of that command, and tied in with authentication, ensuring that whatever entity is issuing that command is authenticated to have the privileges to do so. And so those are the 5 things: implement zero trust, remove the reliance on perimeter, always authenticate, always authorize, adopt PDP, persistent data protection, and have a good cryptographic framework for the authorization of commands. And with that, if there's any time left, I'd love to take some questions. And thank you for listening.